Okay, so when we stopped yesterday, we were on Kepler's third law, which is that if you take the average radius of the planet's orbit, so from the center of the planet to the center of the sun, and cube it, and you divide it by the period of the revolution for the planet, so how long it takes the planet to go once around the sun, squared, it will be equal to a constant for all objects orbiting the same central body. So if we take the radius of orbit for like Venus and we cube it and we divide it by the time it takes Venus to go around the sun once squared, we get some constant. Okay, big deal. But then if we do it for Earth, we get the same constant. And if we do it for Jupiter, we get the same constant. And Neptune, we get the same constant. Okay? So as long as they're all orbiting the same central body, when you do r cubed over t squared, you'll get the same constant. Now, if you did this for Earth's moon, did r cubed of the Earth's moon over the t squared for the Earth's moon, you'll get a constant, but it won't be the same as for the things orbiting the sun. But it would be the same as like the International Space Station if you did its r cubed over t squared. So any two objects that are orbiting the same central body will have r cubed over t squared equal to each other. So this one we don't use very often, okay? But we do use r1 cubed over t1 squared is equal to r2 cubed over t2 squared. We could actually figure out like what speed we would need to give the International Space Station, so like how long it would take to go around if we knew how high we wanted to put it and if we knew the moon's data. Okay, so this is true as long as the objects are going around the same central body. Doesn't matter if the body is the Earth or the sun, but they have to be the same central body. Okay, so this is Kepler's third law. Thing was, Kepler was only a mathematician. He knew this was true. He could prove it with the data, but he had no idea why it was true. It took Isaac Newton to come along after Kepler did this to figure it out. And Isaac Newton said, well, I know that Fg has to be equal to Fc, which means G m1 m2 over r squared, and it's a capital R because it's the radius of orbit, must be equal to mv squared over r. So one of the r's is going to cancel, and one of the m's, and the m that cancels is the one that's doing the orbiting, right? Think back to circular motion. This was the mass of the thing we were swinging around our head. So the m that's left is the central body m. Okay, and so one of the equations we get from this is v squared is equal to g mass of, and I'm going to put a cb here for central body, over r. Central body. So we can use this equation to find out what speed an object must be going if it's orbiting a central body and we know its radius. Okay, and we say must be going so that it doesn't end up being sucked into the planet or going off at a tangent to the circle. So this is one equation. That's also one. Now remember that v is equal to 2 pi r over t. So if we take this and substitute it in where the v squared is, we would get 2 pi r over t squared is equal to g mass of the central body over r. So 4 pi squared r squared over t squared is equal to g mass of the central body over r. So I could bring my r up so they're together, and maybe I'll take my 4 pi down, and I'll get r cubed over t squared here is equal to g mass of the central body over 4 pi squared. R cubed over t squared is what Kepler had. This is one side of Kepler's law. Now look at the other side. G is a constant. It never changes. The mass of the central body is the same as long as they're all orbiting the same central body. 4 is a constant and pi is a constant. This is the constant that Kepler found. So why are the r cubes over t squared the same for everything going around the same central body? Because they're equal to the universal gravitational constant, the mass of the central body, divided by 4 pi squared. Okay, so this equation is known as Newton's version. Newton's version of Kepler's third law. Okay, so if it says something about use Newton's version, it means this. So what equations do we have then to use in this unit? Well, we have our centripetal ones that we already knew. Fc is equal to mv squared over r from the last unit. I'm going to put a capital R there just because. And AC is equal to v over r. And now we also have from the other day, Fg is equal to g m1 m2 over r squared. And because of that, we also know Fg is equal to mg. And that means that little g must be equal to gm over r squared, where this m is the central body. And this m is the one in the field, okay? And then today we just found r cubed over t squared of one object is equal to r cubed over t squared of a second one going around the same body. And we found v squared is equal to g mass of the central body over r of the planet. Oh, and from the other earlier we knew v was equal to 2 pi r over t, right? The circumference over the period. And then the last one we had was r cubed over t squared is equal to g mass of the central body over 4 pi squared. Okay, so these really are all our equations. Maybe just another little note, this AC is really little g, right? The centripetal acceleration that keeps the object going in the circle is also the acceleration due to gravity. So AC and g are really interchangeable here. Okay, so today I would like you to use some of these equations, and actually we'll be using them for the next few days. But for today, page 586, numbers 9 to 13, please. Okay, and the key would be write down your givens and then write down these equations and say, okay, which one can I use to solve this? And the more you do, the easier it'll get. Okay, so try these ones for this evening.